We're going to take our first exploration into collections in Python. And by collections, I mean groups of things that belong together. And the first collection we're going to look at are strings. So strings are immutable sequence of characters. And this immutable is going to be a key point when we talk about other collections. And what we mean by that is once you've defined a string, you can't change its value in the program. So, and I'll illustrate that in a minute. So strings are specified using either a single quote or double quotes. It doesn't matter which you use, convenience based on the strings you're typing. And as I mentioned in class, I find this problematic because I'm not consistent in my use of single versus double quotes, and thus have messy code to edit when I go to clean up or change things. Python also allows you to use triple quotes, that either with single quotes as I show here, or triple double quotes as I show here. And so this becomes useful for strings that have quote symbols or strings that have line breaks, things like that. So the triple quotes becomes a very useful format for writing very generic, for creating very generic strings. Strings, how Python works with strings has been my biggest challenge migrating from Python 2x, like most recently Python 2.7, to Python 3 versions. And I mention that simply because if you were using Python 3.5 or 3.4 in the class, there may be applications that you work with that require Python 2. And other than like the print function, the Python 2, you can use print as a statement. Strings are really the biggest kind of underlying difference between Python 2 and Python 3. So here are some examples of creating different strings. So here I'm creating a variable named Zeus, and it's a string specified by double quotes. Here I have a variable named Apollo with its value of Apollo indicated by single quotes. Here's Poseidon, where I'm using triple single quotes. And here is a string, a variable text1, where again I'm using triple double strings. And the reason I want to do that is because my string contains a quote. In this case, I wouldn't want to drive this bus myself. So that becomes a useful thing. Now there is going to be a caveat here that we should explore. And here I'm doing, I could have achieved the same purposes with a single quote because my text only includes the double quote, so it could be created without ambiguity. So let's evaluate this cell. And both things print out fine. Here I have a triple quote sentence, and now I have both a double quote and then a single quote in terms of like a apostrophe. And let's evaluate that. So that works out fine. But what if I were to take, let's take this text1 that, see I have a space here. Let me add a cell. And I'll just call it text3. And let me eliminate that. So what we have here, you see we start our quote off with a triple quote. We have a single quote here that ends that starts the quotation. Then I have a single double quote that ends the quotation and a triple quote that ends the string. So let's see what happens. I get an error. And the error is because Python isn't thinking in terms of, oh, I have a double quote that's starting a quotation, so I should be expecting a double quote to end the quotation. It's just going along, and it's reading here, and it sees a quote, it sees a quote, it sees a quote, and so it's saying, oh, this terminates a string, and then there's this extra dangling double quote and it doesn't know what to do with. So it starts a new string, but it doesn't end, and that's why we get this end of line while scanning string literal. We started a string, but we didn't end it. And so I would need to do that, and that gets us back to valid Python syntax. Okay, to understand kind of what these issues are between Python 2 and Python 3 with strings, we need to know a little history about characters and computers. So as I've mentioned before, computers are essentially transistors, and they can be, transistors are on or off. They have a high voltage or a low voltage, which we interpret as 1 or 0 on off. And this naturally translates to numbers. So how do you get computers to represent characters? So essentially what we need to do is we need to map numbers to characters. And kind of the most important first standard for this is referred to as ASCII, which stands for American Standard Code for Information Interchange. And I have a link here to a Wikipedia description of it. So the first standard was published in 1963, and it had 128 characters corresponding to 7 bits, based primarily on the English alphabet. And here is an early code where you see we've got some special, we got a space, we got exclamation point, we got some punctuation here, and these are various control characters like a line feed, a backspace, etc. And then we have the very last character is a delete. We have our numbers, we have our uppercase letters, then we have our lowercase letters. So but essentially what we're going to do is we're going to take the number 0 and we're going to map it to a null. We're going to take the number 1 and map it to SOH, which I can't remember what it is, and so on. So we have 128 characters that map to the numbers 0 to 128. Well, there's some obvious limitations here, and that is that the world isn't all written in English. And so kind of while America in the 20th century was clearly the dominant economic and technological force in the world, ultimately this becomes very limiting to only having your computers a representation of these basic punctuations and English alphabet. And so people started writing other character coding systems, and what we use now is known as Unicode. And again, here's a link to a Wikipedia description of Unicode. So the latest version of Unicode contains more than 120,000 characters, a far cry from our 128 in ASCII, covering 129 modern and historic scripts as well as multiple symbol sets. What kind of helps us out a little bit is that the first 128 characters of Unicode are ASCII codes. And so you can view ASCII as a subset or Unicode as a superset. But we can more or less move easily from ASCII to Unicode. Going the other direction doesn't work necessarily because you have the more Unicode characters than you have ASCII characters. In Python 2 version, strings were by default ASCII, but you could create Unicode strings. Now in Python 3, all strings are Unicode. And so that's going to just add a layer of complexity in working with strings in terms of, and we're not going to mention this here, go into detail on this here, that there's different encodings that Unicode can use, the most common of which is UTF-8. But just more complex to allow representation of a larger character set. Okay, so in summary, we have characters are represented by numbers, and so there's a mapping from a character to its underlying numeric representation, and there's also going to be a mapping from the number to what character in the encoding does it correspond to. And so Python has two functions that do this for you. The first is ORD, where it takes a string and returns the decimal value that corresponds to that string. So this is the basic comparisons of strings. So if we ask if A is less than B, what Python is asking is the number that A corresponds to less than the number that B corresponds to. Okay, similarly, there's a car function which takes an integer and returns the character that corresponds to that integer value. So here are some illustrations of it. So here I'm going to ask which character corresponds to the number 89 and which character corresponds to the number 5,674. And so we see we have a y. Okay, I'm just going to take a pause here and close my email so I don't keep getting the messages popping up. And the character 5,674 corresponds to this, whatever this is. Okay, again, I can take an ASCII, a Unicode character, as I have here, and I can ask which number does that correspond to, and that corresponds to number 339. And I can take the letter lowercase a and see that that corresponds to the number 97. So when I'm doing a comparison, I'm comparing their ordinal values, and if we look at here and I ask, is a lowercase a less than an uppercase a, we get false. And this just requires reference back to here, where the uppercase letters are defined first in the code, and then the lowercase letters. Okay, so once we've defined a string, how can we access it? So strings are an example of a sequence, meaning that they're a collection that has a natural order to them. There's a first character in the string, a second character in the string, and so on. So we can access individual characters in the string with square bracket syntax. And this square bracket is going to show up very frequently in all the different collections that we use. It's important to remember that Python sequences start at 0, not at 1. So if I want to access the first element of a string, I'm going to use a 0 and not a 1. And this could be something that can trip people up to start with. Okay, so that's the indexing access through the square brackets. Kind of an extension of this is slicing, and that's where we're going to access chunks of the sequence or the string all at once. And so the notation for slicing, again, uses these square brackets, but then we specify a starting position in this string, a stopping position in this string, and an increment value, and these are separated by colons. So square bracket, a starting index, colon, a stopping index, colon, and an increment or a step size. So some highlights here. First off, the starting is inclusive. So the number that I use here at start is going to be included in what slicing returns to me. But the stop is exclusive, meaning I'm going to return the pieces of the string starting at start and up to, but not including stop. So let's try some illustrations of this. Looks like I repeat myself here. So I have this text 2. I heard her say to the driver, I wouldn't want to drive the bus myself. So if I want to access the first element of it, which is I, that's done with index 0. Now I'm going to do slicing. So I'm saying return to me all the characters in that string starting at 0 and going up to but not including 13. And that's, I heard her s, and you see that the 13th character is actually the A in say, and that was not included in what the slicing returned. Okay, let's do some more examples here. In that the start and both the start, stop, and increment have default values, meaning that if I don't specify where to start, Python's going to assume that I want to start at 0, the beginning location. If I don't specify an ending location, it's going to go up to and include the entire string. And if I don't specify an increment, it's going to say you're going to take every consecutive character. So let's look at that here. So here, on this first line, I don't specify a beginning. So it's going to start at 0, and it's going to go up to, but not including 11. Here, I specify a start, but no end, and no increment. So it's going to start at the 11th character, go through the return to the inclusive end of the sequence, and it's going to take every character. It's not going to skip over anything. In this third example, I don't specify a start, so it'll assume 0. I don't specify an end, so it'll go all the way up to and including the last character in the string. And now I specified the increment, which is 2, so it'll take every other character in the string. So let's see what this looks like. So I heard her say to the driver, so on. And you can see here that the third one is kind of becomes nonsensical as we skip every other character in the string. Okay, so this slicing is a syntax that we're going to use in a variety of collections, including strings, lists we'll talk about in a second, tuples, and most importantly, probably for a lot of the work we do, NumPy arrays. Okay, so strings are objects in Python, and that means that they have attributes and they have methods. And we'll go into this in more detail when we talk about object-oriented programming. But for now, think about attributes as nouns, things that strings have, and methods, think of them as verbs, things that strings do. And you can access the attributes and methods that a string have using the dot notation. And you can learn about the attributes and methods with using tab completion and the help function. So here's an example of what I mean by the dot notation. So we have our string, text2, and then I type a dot, and then I can specify, in this case, it's a method, and a method is a function that's attached to that string. And so functions have opening and closing parentheses. So text2, which we were printing up here, is not uppercase. Not all the characters in it are uppercase characters, so that returns false. I can ask the help about a particular attribute or method. So here I'm asking about the method is alphanumeric. And so we can read here that this returns true if all characters in S are alphanumeric and there is at least one character in S, false otherwise. So if we think about this, these are all alphabetical characters except for our punctuations, like our commas, our period, and our quote symbols. So if I run this, we should expect the return value to be false, which it is. Now let me, like the tab completion, insert cell below. If I take text2 dot and then hit tab, this window is going to pop up, and these are all the different attributes or methods that this string has. So I can ask, let's see. Most of these kind of make sense. Upper converts all the characters to uppercase. Swap case switches lowercase for uppercase and vice versa. Strip will strip out leading white spaces at the beginning and end of the string. Right strip strips white spaces on the right side. So on. We'll explore some of these, but you can see that just being able to hit dot tab becomes very useful for learning what you can do with this variable text2. So in this case, I heard it's going to take every beginning of something and make it a capitalized, like the beginning of a sentence. If I want to convert everything to uppercase, I can do that. Split. It's going to split on white spaces and return a list. So again, one of the ways to really kind of get a handle on this is just experimentation, either in the notebook or in a Python or IPython shell. Okay, so there is a string module in Python that defines functions that more or less correspond to all the methods that a string instance has. We won't go into more detail on that at this point. So what kind of things do you want to do with strings? Generally, we want to extract information from them, and extracting that information can be facilitated by essentially kind of a pre-processing of the text before we do it. So if we're looking for a particular word in the string, maybe we want to convert everything to upper or lowercase because Python is case sensitive, and if something starts with an uppercase letter, that's different than the same word that doesn't start with an uppercase letter. We'll want to do things like recognize punctuation so that we can split sentences up. We want to check and see if a substring is in the string. We might want to check and see whether we can take that string and we convert it to a number, etc. So let's go down and explore some of these. So let's look at split. So split is a method, so it's a function that's attached to an instance of a string that will take that string and split it into parts and return those parts in a list. So here I've created a string that's just the numbers 1, 2, 3, 4, 5 separated by commas. And I'm going to ask Python what the split method does. So it returns a list of the words in the string S using a separator, which I can specify, I don't have to specify, as the delimiter. I can limit to how many pieces I want to return, etc. Key point here, if I don't specify what I want to split on, that's this sep or separator variable, then by default Python will split on white spaces. So here I tell it to split. It's going to split on white spaces. There are no white spaces, meaning a space, a tab, or a new line in the string. So what I end up with is a list with the original string in it. If, rather, I provide the comma as what I'm going to split by, then you see now I have a list of the individual numbers that were in our string. The comma in this instance is what's separating the elements of the list and not part of the individual strings. Okay, so here's a note from a progress note, an MD note from the Mimic database, and I can print out what I split. And so you see now instead of a string, I have this list of these individual strings that were separated by white spaces. Okay, there's kind of an inverse function of split, and that's join. And that will allow us to take a string and we're going to join together things from another sequence. So here I'm going to create a variable number list, which I obtained by splitting my string A by commas. And then I'm going to explore different ways that I can join it together. So here, this is an empty string. I have an opening and closing quote with nothing in between it. And I'm just going to split the cell here. Split cell. Let's run, see what that looks like. Okay, so you see that's joining all those pieces together because it's joining all those individuals. Let me print number list. So I have this list of numbers. It's joining them all together in a string with nothing in between them. Here I got a space. So I'm joining, and now there is a space between each one of my numbers. Oops, wrong place. Didn't need to do that, kind of got out of place here. So let's just go ahead. Here I'm going to have joining with a comma, here a comma and a space, and here I'm just taking this sentence fragment. And if I run this together, I get what my original string was, commas in between each of them. Here I have a comma and a space in the string. And here I have 1, this will look messy, 2, this will look messy, 3, this will look messy, etc. So I can take arbitrary things that I want to use to join, to separate the pieces when I join the elements from the sequence together to form a string. And so this will be, I might use a bar, whatever kind of delimiter I want. It's arbitrary of what I put in here in this join function. All right, string, let's see, for preprocessing and modifying. Okay, that's a trick heading that since strings are immutable, we can't modify a string, but we can take a string and return a new string with the changes made to the original string. So that's what's happened with the lower and upper. And there's also a replace where I say take some characters A in the string and replace them with characters B. And again, these are all going to return a new string. The original string is going to be unchanged. So here I again have another note from the Mimic database, and I am going to convert note 2 to upper. Let me put a split here. And I'm just printing out, this is a replication, which we saw in class last time. And then at the end, I'm going to print note 2, and we'll see that note 2 is unchanged. So here here's our original note 2, here's rendering it all in uppercase, here's rendering it all in lowercase, and here you can see note 2 as a variable is unchanged. These did not change the string itself, but returned new strings. So here, swap case, here I'm going to replace A's with Z's, and here I'm going to replace spaces with an empty string. So this is essentially a way of deleting spaces from our text. And here we get our swapped case. Here we'd have to read through it and looking for any place where you're expecting a lowercase a. And like today, we now have Todd Z. And after became Zafter. And here we've just stripped out all the spaces from the string. Okay, here are methods that come with the strings that allow you to ask questions about it. So we already saw the is alphanumeric. This is digits or letters. Is alphabetical? Are these letters? Is digit? Does this represent a number? Is space, or are these white spaces? And you'll see true, false, true, false. It's not a space. It is a digit. It is alphanumeric. It's not an alphabet letter. Here are some of our spaces, like /n. This is how this is called an escape. So we're using this backslash to escape n. This means new line. A backslash t means a tab. And so if we ask, is a new line a space, is a tab a space, we should get true. Whereas the letter B, if we ask it if it's a space, that should be false. But if we ask, is the letter B an alphabetical character, we should get true. which we get here. Okay, our last topic, not quite our last topic, this is a long video, is string inclusion. So we can use this statement in to ask whether string 1 is in string 2. And it'll test whether string 1 can be the string 1, which we're asking is it a subset of a string 2, and does it occur anywhere in string 2. So here I've given you an actual radiology report of mine from a poor skateboarding injury I had a few years ago. And it's about my shoulder. And so we're going to ask, are different versions of shoulder found in the report? So a capitalized shoulder is not in the report. A lowercase shoulder is in the report. An uppercase shoulder is not in the report. But if we convert report to an upper, then we can find that in there. Okay, find is going to not just tell us whether a string is in a substring is in a larger string, but where it occurs. So what's the index of the first location, starting location of that string at. So we can look at the help here. It's going to give us the details. And so what we're going to find is if the string is not in the parent string, then it's going to return a -1 on failure. So let's look at this. So I'm going to ask if edema occurs in the report. I'm going to convert the report to lowercase and then ask if edema occurs in it. And then I'm going to ask if pituitary occurs in it. So we would expect edema to possibly be present in my shoulder MRI report, but we would not expect pituitary to be in there. So here we get, yes, edema occurs at position 794, but when we search for pituitary, we get a -1. Index behaves very similarly, with the one exception that if the string is not to be found in the parent string, then instead of returning a -1, it's going to throw an exception, which is an error message that halts the program unless it's handled. So here we get the report, the help on it. So now I'm going to use index to tell me where the occurrence of shoulder or carotid occur in the report. So you see that shoulder first occurs at position 108 in the report. But when I try to search for carotid, carotid is not in the report, and so I get this exception, which in this case is a value error. And it tells me the substring is not found. Okay, so this is going to be nice for genomic sequences where we have sequences of these characters, ASCII, TG. And so I've defined the sequence, and I can have a little cell here where I'm asking you to enter a subsequence. So, and we're going to check to see whether it's included in the string. So if I do A is in it. I can run it again, AA, ACT, false, ATC, true. All right. Okay, final topic, and that's string formatting. Oftentimes we, either for output to a file or to the screen to present the user information, we want to create strings where we're taking values from some of our variables and putting them into strings. And so Python has a C-style way of formatting, and this is usually referred to as string interpolation, where we're interpolating or putting into the string other values. There's a newer method with the format, which I have an example here. I don't ever use this. I grew up as a C programmer, so this is how I know how to do it. And so essentially the C style, you have a percent symbol saying, aha, we're about to put something in it, into the string, and then you can have, so a %S says, okay, I'm going to insert a string in. A %D means I'm going to insert an integer in. A %f means I'm going to insert a floating point number. And then for the floating points and the integers, I can specify characteristics of it. So I'm going to say I'm going to use 3-digit spaces for the number. And if the number has less than 3 digits, then I'm going to fill it with zeros, pad it with zeros. And in this case, I'm going to say, well, I'm going to use 5 digits, and 4 of them are going to be following a decimal point. If Python needs to use more than this, it will to represent the number, but it will. So this is basically saying use at least 5 digits, 4 of which should be decimal points to the right of the decimal. So let's show this. So we had the string, the values of pi is, and I had %5.4f, and I told it to insert the value of pi defined in the math module. And you see here we have 1, 2, 3, 4 decimal points and 5 numbers. Here, if I can scroll over, I have the number 7 that I'm inserting into the string, but because I told it to use 3 digits, and if the number had less than 3 digits to pad it with 0, I get the 007 as the output.